Thanks, Brian, for a kind introduction. Hi. Hi. My name is Shinpei Kato. I'm an associate professor at the University of Tokyo and Nagoya University. I'm also a founder and CTO of Tier 4, which is a Japanese startup. So I'm really happy to be here, and thanks for giving me this opportunity to give a presentation about Autoware, which is ROS-based open source software for self-driving mobility. So we are expecting to have autonomous self-driving vehicles in a city rather than a highway. So this is what we are looking for. To this end, we're working on sensing and perception using, for example, LiDARs. And we also really interested in building 3D map, high-definition 3D map, to understand which position we are driving on. The system must be embedded, and perhaps recent trends is AI, including navigation and planning, to make the vehicles drive by itself. Today, I'm going to introduce our activity about how to build such an autonomous self-driving vehicle using ROS. First, I want to mention that we don't really look for highway driving. We look for urban city areas. And perhaps the velocity which we target for is about 40 miles per hour, not 100 miles per hour. And this is the most important thing. So our software is still R&D stage. So safety is not yet certified. So if you want to use this software, please take your own risk. OK, to use our software, what we need? A vehicle and a couple of sensors. So Autoware is a platform. It doesn't really dedicate to specific sensors. You can choose which sensors you want. For example, we often use 3D LiDARs, Velodyne or ZIG, Ibeo, and so on. And cameras, GPS, IMU. Mostly all types of sensors are currently available with our software. And you may need additional modification to the vehicle because you have to connect your computer to the vehicle so that you can control. This might be tough engineering, but I'll explain our partner at the end of this presentation so that you can get easily the platform and you can immediately start field testing by using our software and experimental vehicles. So our software has a couple of options like accessories, including smartphones, or we can also connect nice displays using RVs. RVs is the most useful tool so far. We have really appreciated. Yeah, and this might be a little bit tough thing, as I mentioned earlier. So we need a little bit modification to the vehicle so that the computer can send commands to the vehicle. And this can be provided by a partner company, which I explain later. And so Autoware originally was developed on a laptop or PC, but recent version upgrade enabled us to use embedded vehicle platforms. Especially, we're happy to use NVIDIA's GPX platform. Actually, we have hardware here. So I'll make some demonstration at the end of my presentation. By using this platform, everything is actually running on this kind of small vehicle platform. Don't use any other computers. Car is controlled by a computer. We use 3D maps to determine which lanes to go, left and right hands on the intersection. We can also detect objects and recognize the traffic lights. And of course, turns are pretty stable. So immediately you can get, so once you get this platform, you can immediately do the same experiment. On the day, I guess, you get this platform. We not dedicated to specific vehicles. Actually, we have a lot of vehicles that we worked on so far. It's a Toyota vehicle, nicely decorated inside. We also like to decorate the car because some VIP people, show up and sometimes they take on a ride. And not only test course, we go on the public road. No support cars. Everything is in real. And we do this demonstration under the permission from the police. And the driver is not controlling the steering, axle, brake at all. I would say this demonstration got a success maybe 8 times out of 10 times. Because this is still R&D stage. That's why we still need a driver to be ready for overtaking the vehicle's control. But this quality, we believe that this is really useful platform. Once you get this platform, you can do this demonstration on the spot. So you can save a lot of time and money in order to start this kind of project. And we don't choose car. So our software also works on golf cart. And you can see that strange, funny shape box on top of the roof. Everything is inside. You don't really have to put computers, cameras inside the vehicle. You can put everything on this box. It's not free. And buggy as well. So basically, we have made a lot of experiences in many types of vehicles. The thing is that we use the same software. And tuning happens, of course, for individual vehicles. But this tuning doesn't really change. Some parameters may be different, but the same persons, same approaches, same experience can be applied for all the vehicles we have worked so far. And many vehicles. And perhaps this is the most significant feedback for us, which happened recently, is so Udacity has made a demo driving from Mountain View to San Francisco, including a lot of traffic lights and crosswalks. It seems that they have driven over 30 miles. We really appreciate that not only us, but other users do similar demonstration using a software, and we get a great feedback from them. Like I'm going to explain later, but we need to use 3D map to use this software. But 30 miles, 3D map, so huge. So we got a problem, but we can fix it, and we can move on. So if you are interested in software, we really appreciate that you can use actually the software and give us a feedback. That's really appreciated. OK, so I'm going to talk about some details about our software. Basically, we provide almost all functions necessary for self-driving autonomous vehicles, including localization, detection, and some prediction, decision-making, control, and so on. And this is implemented by ROS. This is example of localization module. It is composed of 6 modules, 6 packages right now. You know TF. Somebody likes TF, somebody doesn't. Yeah. So this is one example of how we implement our software by using ROS. So to use our software, there is one more important item to be ready before using software, which is 3D map. And we can use our software to build 3D map. But as you may know, SLAM, which is a robotics approach to build a 3D map, sometimes doesn't work in real urban environments. So we suggest that we use special measurement vehicles to collect data of the city. This is what we can get from that vehicle. So this is a point cloud with RGB, very high resolution. We can create this 3D map just in a week, because it used to take a month, but after a lot of experience, we could accelerate the activity, working time. And this is so high resolution that if you're human, you can easily understand which is a white lane, which is a zebra. But for computers, sometimes difficult to recognize which is a white lane, especially in real time. So what we do is to extract the information from the point cloud before we operate the vehicle. This can take time, for example, a few days, because it doesn't have to be real time. Once you extract the information, all the necessary information from the point cloud, you can put this information back to the original 3D point cloud. Now, the 3D map has two different layers. One is point cloud, which represents the shape or structure of the world. The other layer is kind of a vector, which represents the semantics of that area. For example, where is the lane, how the intersection is connected, and where is the traffic light. For details, for example, where is the pole, and so on. Basically, all necessary information for driving can be embedded in this 3D map. So we call it high-definition 3D map. This is the most important item for Autoware to work correctly. And how we can use this 3D map? What often happens to us is using LiDAR, because LiDAR scans the point cloud. Do you know these LiDARs? I have all of them. So LiDAR is nice in the sense that once you capture the data, it can be expressed by point cloud. To be more precise, point cloud 2. It's a new format. So because this is abstracted, we can actually use any LiDAR sensor so far. One can be very high dense and can reach long distance. One cannot. It depends on the situation what kind of situation. So you are driving, for example, in a campus, you may not need to use the LiDAR that can reach long distance. So you can choose which LiDAR you want to use. And Autoware provides a couple of algorithms for localization using LiDAR. We often use normal distribution transform, which is a scan matching-based algorithm to detect your position. The concept is simple. We have 3D map. We have LiDAR scan. You compare two different shapes and find the best coordinate which can match both the map and scan data. For example, in this case, the red highlighted arrows shows the position, estimated position of your vehicle. We do this matching every time we get the sensor data. The Velodyne LiDAR, which we often use, has 10 Hz. So we have scan data every 100 milliseconds. So localization must be finished in 100 milliseconds at the latest. But if everything goes well, you can estimate your position very precisely. We don't know how to measure the accuracy of this localization because it's more accurate than the GPS. But we have a sense of accuracy in centimeters order. So we can never miss the center of the lane because the accuracy of localization is centimeters order. And if you find your position, you can also build a map by yourself. This is often referred to as SLAM, Simultaneous Localization and Mapping. And Autoware provides the SLAM function. So if you don't want to use your money for building 3D map by using the measurement vehicle, you can use this approach as well. But unfortunately, SLAM is not very effective for long distance mapping because the errors are accumulating as the vehicle is moving on. So after, for example, 30 miles of mapping, there may be a huge gap between the built map and the real environment. But for campus or test course testing, this mapping function is very useful because you can easily build 3D map by using LiDAR. And Autoware also provides a function to share the position of other vehicles with other vehicles. So it can be connected to the database in the cloud servers that our startup provides. So once you allow the system to upload your global coordinate position, then you can share your position with other vehicles to, for example, estimate the hotspot of traffic and so on. This is not open source, sorry. Server side is not open source, but you can use this system from the open source, our software. So this is about localization and mapping. So next topics is a detection. Detection is, we still don't know what algorithm is the best approach because, for example, deep learning has made a huge leap in detection rate of, for example, image processing, but still it's not perfect. What we often do is first we make some clustering upon point cloud because this usually works. Sometimes if up-down slopes appear in turn, clustering may fail, but we try to improve it. And for now, we don't really see the significant problem in clustering. So once we can cluster the objects, then you don't know if it is a pedestrian, it is a vehicle, but at least you know free space. So as far as you know free space, you can somehow drive the vehicle, but the behavior may not be comfortable. But this is a starting point for self-driving. And if you want to know what they are, then you have to use more cutting-edge algorithms like neural networks. We provide neural networks algorithms. Currently, we use two of them. One is SSD, the other one is YOLO, because their detection rates are better than other algorithms. We try to support more algorithms, because if you are doing self-driving project, the most frequently asked question is, can we use deep learning? I have heard of that question 100 times. Everybody is asking, can we use deep learning? I might answer, for what? So. Yeah, but deep learning is pretty strong. We used to apply deep learning for image recognition, but recently we also use deep learning for point cloud detection, because point cloud is sparse as compared to the images. So it's more difficult to recognize the object classes. But recent academic papers show a few ideas about applying deep learning for point cloud detection. And this is the result of package that Autoware provide. You can see the bottom line. Green clusters, perhaps pedestrian, and red clusters are cars. It's not perfect, yes, but it is getting better and better. So if you train a data set using sufficient amount of data, we expect that the result of CNN neural net detection for a point cloud can be much better. So we are working on it right now. And perhaps this is the most tricky part of software. We like to use both cameras and LiDARs, or maybe LiDARs and so on. But calibration is a most kind of troublesome work, because say for the short distance, yes, it can match the coordinates, camera coordinate, point cloud coordinate. It can be matched in a short distance, but for long distance, sometimes it doesn't go well. But if calibration works well, we actually provide a calibration tool as well, so you can try one. And if it works, then the object detected by cameras can be reprojected on LiDAR coordinates, so that cameras can tell, hey, this is a car, this is a pedestrian. If this function becomes mature, then our software is going to be really close to production quality, because the detection is the most, say, unstable part of self-driving provided by Autoware, because there is no 100% guarantee that you can detect objects. But sensor fusion can improve the rate of detection. So we expect that the Autoware provides more sophisticated ideas, approaches to sensor fusion. But right now, we can do this. And yeah, this is also important. So there is a popular benchmark set called Kitty, which is provided by KIT in Germany. And Autoware can directly lead the data sets from Kitty, so that you can, for example, for academic papers, you have to evaluate your new ideas with existing algorithms on the well-known data set. So Kitty dataset perhaps is the best dataset that you can use for your performance evaluation. And traffic light, I often hear that the most difficult function of self-driving is traffic light recognition. Many car makers, engineers ask how to improve traffic light recognition, because you have to find small red light, small green light from the huge image. Basically, this is a difficult task. So what we do in our software is we use 3D map information. So imagine that you know your position very precisely. So it's a few centimeters accuracy. And you also have 3D map. So you know that where is the next traffic signals appear. So we project 3D map information onto the image so that you can see that now this software in this scenario knows where is a traffic light. You can see undefined, maybe from people in the front can see the text. This means that the software knows there is a traffic light there, but the resolution of the image is not enough to recognize the color. So once the vehicle is approaching, then it can detect the colors. So the benefit of this approach is that you don't have to search unnecessary areas. And even in the scene where we don't have traffic lights, the software knows there is no traffic light because we have a 3D map information. So we don't have to run traffic light recognition function. So we can reduce misdetection of colors a lot by using 3D map. So if you have localization and detection, then you can do the basic driving without controlling the car. But if you want to avoid something, for example, parking vehicles or constructions, then you need path planning. Autoware provides A* based search for object avoidance. It can search for the shortest path or a more appropriate path which can avoid the objects. Right now, we can only avoid static objects. Avoiding moving objects, you can try, but it may not work. In addition to A*, we also support state lattice, which calculates in advance appropriate path, then can choose one. A* searches on the spot, but state lattice already calculated spline pieces, then you can choose the most appropriate lane. Once you determine the lane or path, then all you have to do in the rest is to follow that line. We use pure posit. This is the algorithm to follow the target point, which is highlighted by green cube. For the turn, you have to put the target in the close point. On the other hand, if you want to speed up your vehicle, you want to put the target in a long distance. This is mostly tuning thing. Detection, localization, planning often work, but finally, this tuning we have to do in the field testing many times because parameters are very different for different areas. So we try to look for more kind of integrated approaches so that we can reduce the time of tuning. But once the parameters are selected correctly, then it can drive very smoothly. So we also support some systems tools. You can visualize which CPU cores are used, which tasks are running. Basically, this is realized by ftrace supported by Linux. But we can call directly ftrace from the Autoware so that you can check if the function is working correctly. And you know, end-to-end. Recently, we are interested in deep learning that determines the behavior directly from the sensor data. So this shows deep neural networks predict if the vehicle should put a brake or not by looking at the sensor data. It doesn't really detect objects. So it just read point cloud and camera data and tells you if you should put a brake or not. And the second line is the data from a driving school trainer. So as a result, so deep learning-based prediction can tell pretty similar behavior to driving school trainers. So we think that if we train using sufficient amount of data, then this prediction will be improved significantly in the future. So we are very interested in this approach now. Finally, so we have Autoware, which is now integrated on NVIDIA DrivePX platform. Now it is further integrated in an autonomous vehicle provided by autonomous staff. You can get a vehicle from our partner company, which is autonomous staff. Then you have, of course, lidars or cameras. All sensors you want are already integrated. You don't have to put them by yourself. Autoware is also provided by default, so you don't have to take your time to install Autoware. And the system is running on DrivePX, NVIDIA's DrivePX platform. Sometimes embedded systems give you additional burden in installing or setting up the system, but everything is integrated by default. So if you get this vehicle, then you can immediately start field testing or you experiment using a software. So we're happy to announce that now NVIDIA, autonomous staff, and our startup called Tier 4 are now in collaboration. So this platform will be very soon available. You can check out, for example, NVIDIA's DevZone. NVIDIA is one of the sponsors for ROSCon. Then you can check it later. Now, we can go to some demonstration. So we have the real DrivePX platform. And we don't have any other machines, just one DrivePX, including display. You know, RVs, heavy, sometimes disturb your main functions, but DrivePX has a GPU, which is powerful enough to support RVs. So now he is running Autoware. Can you start? So this is the front screen of Autoware. Then you can choose which ROS bag. Sorry, we don't have a car, so we have to use ROS bag. And play the ROS bag. You don't have to type. You may have some experience in mistyping. So there is no human error, just clicking buttons. Then there is a TF thing. So you have to select the origin of your coordinate. Then there is node list. You can choose which node you want to launch. Just click, 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 click. Don't click both, for example, SSD, YOLO. They conflict. So choose the right one. Then, yeah, there is some parameter window so that you can change the parameters. ROS launch is useful, but you have to open a text editor. And again, you may mistype. So we like slide bars in order to reduce the errors. And 3D map is loaded already. And now localization works. So using 3D LiDAR information and point cloud information are now scan matched. So the vehicle is now recognize his position. Now we can choose lane. Oh, yeah. We can turn on image processing. We use SSD this time. It's one of the most popular deep learning-based algorithm. Sometimes it freezes. I don't know if it's a problem. Maybe RVs. Can you try again? OK. I guess he's trying again demonstration. So yeah. Before we actually we have a poster session where we can show the demo. So maybe we can switch to question.
Yeah. All right.
Thanks.
Thank you for that presentation. And we've got a few minutes for questions. You'll find Q&A mics to your right and to your left. So please feel free to come up to the mic. If you want to ask a question, please do come up to the mic because we're going to record the audio from the questions for the archive. So, and this will go for the whole conference. So as if a talk you've got questions for is happening, then please feel free to come right up to the mics. So, any questions? Any questions at all? Yeah, come on over. And while you're coming over, I'll actually ask Shinpei, do you, so you mentioned it's not safety certified. Do you have a plan for pursuing safety certification? Is that in the scope of Autoware, or is that a user's responsibility?
Both. Because platform must be certified in some sense, but the use of platform is also important. So it's both user and platformers problem. But we provide a real-time capabilities, for example, to ensure or improve the safety of operation. So somewhat is supported. But basically, users can also have to take care of safety.
OK. Yes, first question.
Thank you, Professor. My first question is that which LiDAR do you use for do the mapping for the HAD map?
Can you repeat it again, please?
The LiDAR you use for the HAD map for mapping, did you use the 109 or something else? For
SLAM-based mapping, we use Verodyne, maybe 60 beams or 32 beams, or 64 must be sufficient, but we don't often use that because it's very expensive. So we often use 32 or 16. But high resolution, high definition map, we use measurement vehicle, which installs a lot of other sensors. But basically, if you use our software, then 16 or 32 would be enough.
How many 16 you use?
Sorry?
How many 16 VLP 16 ladder you use per car for mapping?
VLP 16 for mapping.
I think she's asking how many VLP
No,
Just one,
16s.
just one.
Only one, okay.
Just one.
Did you use the intensity for mapping?
Sometimes, but it's not major requirement.
Okay.
Okay, I think we should go to the next questioner, and you can follow up at the poster session, okay?
Okay, thank you.
Thank you. Let's, one last question.
Oh, thanks for building Autoware. It's a very awesome software, that's first.
Thank you.
And I've tried using it, and it runs amazing on the ROS bags. But when I ported it to the real platform, and as you said, it's not final, and I saw issues, one of the questions that I specifically want to know is, how do you take care of the situations of like rain, snow, when the environment it's not sunny outside? Right? Like all the videos on all the ROS bags that I downloaded were of an environment. Do you have any plans for that, or is there work going on towards that part?
Technically speaking, rain, snows don't really matter, but norms might be difficult because LiDARs don't work at all. But my opinion is that in the initial phase of self-driving, I guess we shouldn't operate in bad condition, even though it can perform well. So technically speaking, yes, both using LiDARs and cameras may solve the problem of bad conditions, but perhaps it may take time to make the real vehicle operate in a bad condition in a real city. But technically, it can be, for example, by using sensor fusion of cameras, LiDARs.
Thanks.
All right. Well, thank you again, Shinpei.
Thank you.